Bonjour, mesdames et messieurs. It's a great honor for me and a pleasure for me to present here at useR 2019 in Toulouse. My name is Friedrich Claus Grueber, and I'm responsible for big data analysis for power plant operational data to optimize engineering at Gas and Power Corporation Siemens in Erlangen. Our engineers, they fight with a big amount of data every day. They want to use the operational data to make some design changes, to make some cost out measurements, and they don't know R at all. They don't know either Python or anything else, and they need some useful and understandable investigations and intuitive and easy to use application. Hopefully we do that with Shiny, which I'll show you now. For them, it's the most important thing to have something usable. So here we are in a power plant. You see some components of a power plant, and the first question an engineer is asking, I investigate a component, for example, a main transformer, a boiler, or anything else. And sometimes they start with a low voltage transformer, and the first things they get is a number of signals. And if you have a number of signals, maybe you have 20 signals, the first thing you want to do is you want to find out which plants do match to these signals. So you pull the fleet to the matching signals. That's the first step. Then you have to do a lot of post-processing and cleaning things with the operational data. And then they use our prototype of a Shiny application to visualize and analyze the operational data. So we start with a menu for general settings on the left, and on the right we have some analysis types. It's typically starting with a project and a plant, and you immediately get the signal information like minimums, maximums, means, the validity of the data, and timestamp informations, of course, too. Let's start with a time series. Let's add a first signal. For example, megawatts, we get the time series. Then they add a second signal. They want several signals to be shown in time series. Then maybe they want to get a lower time resolution with a zoom. They zoom into the signals, and they get the zoomed time series for the three signals. Same with the second zoom. Again, you get lower resolutions now in seconds. Let's start with something simple, with the frequency 1D analysis, often used by them, of course. We start again with a signal. We select it. We select the breaks, and we get the frequency and the density curves. Kernel density estimation curves, together with the estimated probability in this region. Here you see something distorting, a data distorting peak, which we don't like. We want to remove it. So we select it, we zoom it, we select it, we exclude it. And we can even exclude several regions which we don't like, because we want only to apply our statistics on valid regions. Okay, this is the second region. Now we have excluded 2 regions. We can do it with several signals. Then we apply it, and we get, of course, another histogram now, which is showing this with respect to these excluded regions together with the probability. Or what they often use is an operation hours distribution. They like it. Engineers like operation hours distributions for their machines. You zoom inside and you get the bigger sight into the data. Okay, or sometimes we need box plots or violin plots, which give us another overview. For example, if we want to see how the megawatts did behave in a 24-hour circle of a day, looks like this. Make it a little bit bigger, use the download feature, it looks like this then. Or you have some daily, weekdays view on the data, or you have some seasonal data with violin plots here, another example. I cannot show all, but some examples here. And of course, the empirical cumulative distribution function, which is used very often, and its contrary, the reverse, to estimate some probabilities for operations. Or in this case, the operating hours view, the accumulated or the remaining operating hour views, okay. But now for something completely different. Let's go to frequency sensitivity analysis. First, we have to select a sensitive signal. We want to see how other distributions react on this signal. We divide the signal in a number of intervals, in 100 intervals in this case, for example. And then we say, then the sensitive signal domain is divided in 100 intervals. You will see it immediately how it works. Then we take one signal and the second signal and the third signal and the fourth signal. And then we look how these signals behave, the frequency plots behave with respect to this interval. And, oh, the first 16 plots were empty. This is boring. It has no data. Why? Because we have excluded already. It's not interesting. Okay, but why? It's because we excluded already an interval of sensitivity signals. But the other signals, they react. You will see it here. You see here the frequency plots with respect to the selected intervals. It's 4 signals, and it's conditioned on the signals of interval 20, 21, 22, and now it changes. The frequency plots are changing with respect to the selected. It's like a conditional probability. It's for the engineer's view to visualize how the frequency plots change with respect to the sensible interval. So it's how frequency plots and kernel density plots vary, conditioned on the values of sensitivity signal intervals. Okay, that was easy, but for them it's a visualization tool. And now for something completely different again. Let's go to 2D statistics. We have started with some easy ones, XY graphs known, but it has no statistical information. That's why we use kernel density estimation. Kernel density estimation is based on a Gaussian kernel here in this case. It shows the correlated signals with respect to colors and to contour plots, which show levels of equal kernel densities here. We can even estimate a probability by selecting a region, and then it's automatically calculated the probability with respect to this kernel density region. So here we see again this distorting region with a summit here inside. We can use this removing bad regions in 2 dimensions as well for several signals. We remove the first distorting region, maybe a second one, then we have a second excluded region, and then the data looks like this. But we won't work with this. I will use a little bit larger one because I want to show you something with kernel densities and sensitivity analysis. So let's use this region. And let's use this for sensitivity analysis with kernel sensitivity. We select a sensitive signal again, and then we slide again into this signal for a kernel density of 2 selected signals here inside. The first 25 were empty again because we have reduced a region, but the next are having data. They have 2D kernel density plots with respect to the sensitive interval, which you will soon see now. It's changing. It's not so exciting because I have had to use a simple example, but sometimes it's more exciting than this. But you see how the kernel densities are changing with respect to this signal intervals. Can do it with other things like ECDFs and so on. So we see how 2D kernel density plots vary conditioned on the values of sensitivity signal intervals. That's it. That's what I wanted to show here. And now, again, for something completely different. Let's see. We want to create an n-dimensional filter now with several boundary conditions. We start with the first signal. We say it should be bigger than 200 megawatts, for example. We can use any kind of operators. And now we take a second signal. We call it, by the way, we call it EBCs, like equation-based conditions. Yeah? Second signal says bigger than 50 amperes. We create a list of conditions. And then we create this, we combine them logically, these things, like EBC1 and EBC2 and EBC3. Easy to understand. Even engineers can handle it really easy. We can do it with OR conditions as well, see, or with any other thing. We can create any logical string. Then, when we have done this, we want, of course, to see how many hits we have. How many records do we have for a logical string? In case of the OR string, it was 3,400,000 results. It's a lot because we have created an OR. And for the end, it's even 1,700,000 records. So we work with this, and now we have created an ND filter, an n-dimensional filter. We can make it more complex, of course. And then we want to see how the frequencies are reacting on this filter. And you see it's a little bit the same because we have excluded the same regions than before. Okay, now to something completely different. We detect a simple event. An event is defined by either a selected condition, what I showed you, EBCs, or a logical string, and a duration. This is new, it's a time duration. Now we look at the time duration of a condition. For example, or a logical string. Here it should be longer than 60 minutes. So we look which time series we will find for this event. So we find here 331 time series, maybe within a year. And they satisfy this event, which we want now to investigate, maybe for pattern recognition. So we look at three signals, and here we see the time series for this event. It's a set, it's a class of patterns which we will then use for neural networks to recognize errors in a plant, for example. You see here different patterns, and okay, it looks like this. So an event is resulting in time series of different time ranges satisfying this event. And this time series we will use as pattern recognition input in our next version of our tool here for engineers. And now again, for something completely different. Let's have a very short look which libraries interfaces were used for our tool. A very short look. Okay, we have used some Shiny library, we have used ggplot, we have used kernsmooth for the calculations, we have used geometry and dplyr for data manipulation, and our application starts with at first clearing the workspace, then we load the work packages, then we set some paths, and then we load a large project list normally. We have some interfaces. You see some interfaces like the title bar, the sidebar, or on the left side of this sheet, and on the right side the main panel, the tab panel, tab-set panel. By the way, if anybody wants these slides, he can have it. He can just write it. So you can see for yourselves which things were used for which thing in Shiny. So we have used other interfaces like select input, you saw it several times, and these radio buttons and action buttons, which we have often used in our application. By the way, it's of course all reactive. This is an advantage of Shiny. We have used conditional panels very often. Here you see a conditional panel which is reacting on the input enabled or disabled. We created a lot of R code dynamically in the background, and this is showing this feature here. So then, of course, the sliders which you saw, the data ranges, the download features you saw, and then, well, some things like text outputs and other things for styling texts and so on. You saw that in the application. And plotting features, a lot of plotting features, input-output plots. We have used the source application to run the kernel code in the background, because we have a large I've created a large packet of kernel code in the background for this Shiny application, which is running with the source feature here, and the notification feature. Then we have this observe user input features, which is observing the user when he's making something wrong. He's putting something wrong inside, and we inform the users that he has to select a logical string to edit, or if anything runs wrong, then the user. Okay, I will stop. It's nearly finished. Only reactive. I just leave a picture at the end of our team, and I'm through. I think I am. Go ahead. No more different. No. Thank you for your patience.
Thank you. One quick question.
Thank you. Sounds like a very sophisticated Shiny app. How did you put your data, or how did you collect your data, or get your data into Shiny, and what's the background? Is it a database, or is it an API call? API call, yes. Yeah. Yes. And in the background of the API?
Yes, I have created I call it a kernel code of this application. It's the kernel code which is running behind. The Shining is on the top. And the data are coming from H5 files, by the way. It's H5 format. First, we worked with text input files, with CSV files and text files, but it's too slow. And then we started to create H5 files for that.
Okay, thanks. Maybe we can talk later on.
Yeah.
Over a bit.
If anybody wants that, I only wanted to say that Ahusha has created the Shiny part, and I have created the kernel. Okay.
Thank you very much.
Thank you.